Hi guys. So today we're going to look at how to solve quadratic inequalities and how to graph quadratic inequalities. We're also going to look at how to solve systems that get into things other than lines. So looking at systems with parabolas and systems with circles. So to start, we're just going to look at how to graph this inequality by graphing just the quadratic at first. Let's make sure we review how to do that. So in order to graph that quadratic, the first thing we need to determine is where the vertex is. So in order to find the vertex, there's two things I can do. If I want to leave it in standard form, then I can use x equals negative b over 2a to find the x-coordinate of the vertex. The other option, I can do completing the square, and then I can rewrite this from that to find the vertex. Now for this first one, let's go ahead and just try and find our vertex using negative b over 2a. So negative b over 2a, that would be 2 over 2 times negative 1, which would give me an x-coordinate of negative 1. Then if I want to find the y-coordinate of the vertex, I'll take negative 1, plug it back into the original, and that gives me negative 1 plus 2 plus 5, which is 6. So then I have a vertex of negative 1, 6. So I'm going to go ahead and plot my vertex. Then from here, I need to get a few additional points on this graph. So there's a couple ways we can get this. Well, one, we know the a value is negative 1. So I can use that a value to determine what my graph will look like based off of how it's transformed from the parent function. So that's one option. Another option, if you want to pick some x values and plug them in. So for example, if I want to plug in 0 and get 0,5 as a point, if I want to plug in negative 2 and find the y value that corresponds there, I can also do that. But I'm going to go ahead and show you how to get a couple other points on here. So I'm going to look at this in relation to the parent function. Well, our parent function, we know, had a pattern based off the vertex. After the vertex and the parent function, the first point we went over 1 and up 1. To get the next point from the vertex, we went over 2 and up 4. Then the next point we went over 3 and up 9. Well, this graph, it's going to be the same typical pattern in terms of how far away we're going. We're just going to go down because the a value is negative 1. So from the vertex, I'm going to go over 1 and down 1. Over 2 and down 4, over 3 from the vertex, and then down 9 from the vertex. So all those points would be on that parabola. So now what we need to remember is we're not actually graphing just the quadratic, we're graphing the inequality. So I need to consider that this is y is less than, so that means it's going to be a dotted line. And then I need to figure out my shading. So very similar to what we looked at with our regular inequalities. If it's less than, we shade below. What we need to consider, though, is when we shade below, we're looking at below the vertex. Then what we need to consider is what's below the vertex inside the parabola or outside the parabola. Since what's below the vertex is inside the parabola, I am going to shade inside the parabola. And that shaded area would be my solution here. Let me make that line a little bit clearer. All right. So now let's look at this next one. I'm going to do this one by completing the square, just so you can see both versions. So if I'm doing completing the square, I need to factor out that 2. I need to leave a blank. So whatever I want to add to that blank, I take the middle number, I divide it by 2, and I square it. So negative 2 divided by 2 is negative 1. Negative 1 squared is 1. But when I'm adding to this equation, I also need to subtract from this equation. The problem is I'm not really adding 2, or 1, I'm actually adding 2 because of the 2 on the outside. So I also need to subtract 2. So then from this point, I can factor. This becomes x minus 1 squared minus 1. Now my equation's in vertex form. So from this point then, I can go ahead and plot my vertex, right 1, down 1. There's my vertex. The a value is 2, so again, that's stretching that graph. So typically from the vertex, we went over 1 and up 1, over 2 and up 4, and over 3 and up 9. But since it's been stretched by a factor of 2, I'm now going to go over 1 and up 2, over 2 and up 8, and over 3 and up 18. So from the vertex, right 1 up 2, right 2 up 8, and then right 3 up 18 is going to be off my graph. And then we've got that axis of symmetry, so it's going to be the same thing on the other side. This one's going to be a solid line. Since it's less than, I'm shading below the vertex. And this time, below the vertex is outside the parabola. So I'm not just shading below the vertex, I'm shading everything that's outside. I'm just using that as a test to figure out which part actually is the solution. So in this case, it's the outside that's the solution. So everything outside that parabola, and also in this case, everything that's on the parabola, because it's a solid line. All right, so now what we're going to do is we're going to look at a system of inequalities. So very similar, we're just going to find where the shading overlaps. So a lot of graphing practice here. All right, so on the first one, 1/2 x minus 1 squared minus 3, that's going to be a vertex of 1, negative 3. It's been compressed by a factor of 1/2. So instead of going over 1, up 1, over 2, up 4, and over 3, up 9, we'll be at 1/2, 2, and 4.5. So from the vertex, I move that amount. Right 3, and up 4.5. And then this one's going to be a dotted line. All right, and then we'll look at our second one. So the second equation has a vertex of 3, 1. It's going to be reflected, and it's going to be stretched vertically. So again, instead of having this pattern from the vertex, I'll be going down 2, down 8, and down 18, which will obviously be off my graph. So right 1, down 2, right 2, down 8. Dotted line. And then the shading, let's consider that. So on the blue graph, all right, so my blue graph, y was above. Well, above the vertex on the blue graph was inside the parabola. So we're going to shade inside this one. Then at the red graph, less than was, again, inside the parabola. So we're looking... All right, sorry, I lost some internet. So again, we're shading inside the blue parabola. We're going to shade inside the red parabola. So we're looking for where the shading overlaps. Basically, the area where I am inside both parabolas would be my solution, which is a very small little section right there. It also says to state 2 possible solutions. So one possible solution that's inside that shaded area would be 3, 0. And it's kind of hard to see another solution, but just remember, all those points that are inside of it would also be a solution. So for example, 3.01, comma 0 would be a solution as well. All right, so if you feel pretty comfortable, pause the video and try B. All right, so on B, the top equation has a vertex of negative 3, 2. It's been reflected and has a compression of 1/4. So instead of following that same pattern, I would go down 1/4, I would go down 1, and then negative 9/4, which is like 2 1/4. But basically going over 2 and down 1 is going to give us enough points to be able to see this graph. Now, if you wanted to on this graph, because it's pretty easy to see the p-value, your p-value here is 1, which means your focus is here. You could use the endpoints of the lattice rectum there to get the rest of your graph. That's also a way you could graph this. All right, so this top equation should be a solid line because it's or equal to. Then let's graph the bottom one. That one has a vertex of negative 1, negative 2. It's going to be not stretched or compressed, so over 1 and up 1, over 2 and up 4, over 3 and up 9, and then this one's going to be a dotted line. Then we consider our shading. So for the red graph, I'm shading above the vertex, which in this case is outside. For the purple one, I'm shading above the vertex, which is inside. So I'm looking where the shading overlaps, that is inside the purple and outside the red, which would give me this solution right here. All right. So now we're going to look at how to solve these algebraically. So a little bit different. What we need to look at when we're solving these algebraically. So if we consider what this question is actually saying for the graph. What this question is saying is, when is the graph x squared minus 3x minus 4, when is that below the line y equals 0? Well, this graph is below the line y equals 0 in that section right there. And what's true about all those points is all those points have negative y values. So what this is really asking is, when is this function negative? So in order to figure that out, what we need to find are the x-intercepts, because the x-intercepts are the only places where your graph can change from positive to negative. So if I can find those x-intercepts, that can give me the range basically of where this graph could be positive or negative. So I'm going to start by finding my zeros here. So I'm going to go ahead and factor. So that gives me zeros of -1 and 4. What I'm going to do is I'm going to plot those on a number line. So what this number line is going to create are 3 different possible intervals for my answer. So one place is everything to the left of -1. One place is in between -1 and 4. The other place is everything greater than 4. So what I'm going to do is I'm just going to figure out, is each of those intervals, are my values positive or negative? Because what I have to do is, it doesn't matter what the actual value is, it just matters if it's positive or negative in that point. Because if one point in this area is positive, every point in that area is positive, because the only way for it to change from positive to negative is to cross the x-axis. And the only place it can cross the x-axis are the 2 places we've already listed. So I'm going to pick a test point. So something over here to the left of -1, let's say I pick -10. If I plug in -10 for x, it doesn't matter what the actual number is. We just care if it's positive or negative. Well, -10 minus 4 is a negative number. -10 plus 1 is a negative number. And a negative times a negative is going to be a positive. So that means everything in that region then is going to be positive. All right, so then we'll pick a different test point. We'll pick one in the middle region. All right, so if I pick some point in the middle region, like 0, if I plug in 0, 0 minus 4 would be negative. 0 plus 1 would be positive. A negative times a positive is going to overall make that section of the graph negative. Again, it doesn't matter what the value is, we just care that it's a negative number. Then I'll pick something on the right side, so something in this region. I can pick 1,000 if I wanted to. 1,000 minus 4 is positive, 1,000 plus 1 is positive. A positive times a positive is a positive number. So everything to the right of 4 in this graph is going to be positive. Once I have this little sign chart filled out, what I'm going to do then is I'm going to figure out, where is this graph less than or equal to 0? So when is this graph negative? Well, the interval where it's negative is from -1 to 4. And then since it's or equal to, I need to include brackets. So that tells me my solutions would be from the x value of -1 until the x value of 4. All right, so on this one, we did this in class. We went ahead and entered the zeros on Pear Deck, but we'll just go ahead and work this one out. So the first thing I need to do is I need to set it equal to 0, and then I can factor. So if I want to factor by grouping, I would do what multiplies to -20 and adds to -1, split my middle, so -5x plus 4x minus 10. Out of my grouping, x comes out, 2 comes out. So the factors that I'm left with which means that my zeros then are -2 and 2.5 or 5/2. So then at this point I'll pick my test points. So picking some negative value, -70 plus 2 is negative, -140 minus 5 is a negative times negative will make this entire region positive. Picking a test point in the middle, like 0. 0 plus 2 is positive. 0 times 2 minus 5 is negative. A positive times a negative will make that region negative. And then picking some value over here, well then that would be positive times positive, which overall makes that entire section of my graph positive. The original question wanted to know when it was greater than or equal to 0. Sorry, just greater than. So my final answer here would be from -infinity to negative 2, and then from 5 over 2 to infinity. So those are all the possible x values that would make that inequality work. So now you're probably starting to notice a pattern here where a lot of these are positive, negative, and positive. Now, that is the case for a lot of these graphs, because if you think about the equation, if the a value is positive, wherever I graph it with that positive a value, it's following the same pattern. It's positive until an intercept, and then it's negative, and then it's positive again. So something that would change that pattern, one thing that would change it would be if the a value was negative. So if the a value was negative, that graph would be opening this way, so it would be negative and then positive and then negative. So keep that in mind. If your a value is negative, that's going to look different. Something else that's going to change that is if the vertex is one of your points, or one of your x-intercepts. So if your vertex is your x-intercept, keep that in mind. There's really only going to be one region there, and then after that, your graph is going to go in the same direction. So both those signs will be the same, whether they're positive or negative. All right, so let's look at another one. So x squared is greater than or equal to 25. So I can solve this the same way I've been solving it. Set it equal to 0 and factor. Find my zeros, make my sign chart. Pick your test points. You're going to follow that same pattern. It's going to be positive, negative, and positive. Original question wants where it's greater than or equal to 0. So that would be from negative infinity to negative 5 with a bracket, and then from 5 to infinity. Now the reason I want to show you this one though is because if you look at it too quickly, it's possible to make an easy mistake. So if you were just trying to solve this equation, let's say you looked at it pretty quick and you decided to square root both sides. And then I said, well, x is greater than or equal to 5. Problem is that's not the only part of my solution. The reason it works out that way, even if you said plus or minus root 5, that would actually give you a wrong answer because it's not all the values where x is greater than or equal to 5. The reason it works out the way it does is because when you take the square root of x, you need to consider the square root of x isn't just x. The square root of x is actually the absolute value of x. So that's the inequality that you're actually solving. So I'm actually doing x is greater than or equal to 5 and x is less than or equal to negative 5. So that's why I think it's just a little bit easier if you set it equal to 0. All right, so now let's look at C. Again, set it equal to 0 and find your zeros. In this case, it doesn't factor, so we either need to do completing the square or quadratic formula to find my zeros. So I'm going to do quadratic formula just so we can work on simplifying. So this becomes negative 4 plus or minus the square root of 16 plus 12, which is 28 over 2. Now, common mistake here, a lot of people will want to go ahead and just simplify those two numbers. You cannot do that at this point. We have to simplify the square root before we do that. So that square root can simplify. So now, once that square root is simplified, now I can go ahead and simplify this, because the only way I can simplify anything with that 2 in the bottom is if both of those numbers are divisible by 2. In this case, they are. So this becomes negative 2 plus or minus the square root of 7. So those are my two solutions that I'll mark on my number line. So this is negative 2 minus root 7 because that's smaller. Negative 2 plus root 7 would be larger. If you're having trouble finding a test point here, again, think about what the graph would look like. Since this graph opens up, the vertex would be down here. And then that part would be positive and positive. So then my graph here, at this point, I'm looking for where it's less than 0. So I'm looking for the negative values, parentheses because it's not or equal to. And that's my solution. All right, so then finally let's look at D. So D, let's try quadratic formula again. And you'll notice the discriminant here is negative. Since the discriminant is negative, I'm not going to have any real numbers, real solutions. What that means then doesn't mean that my equation has no answers. What it means is that this graph is not going to have any x-intercepts. So now what we need to consider is, what does the graph look like, and what is my question asking for? Well, if this graph doesn't cross the x-axis and it opens up because the a value is positive, that graph is going to look something like this. Now we need to look at how that graph corresponds to what I'm looking for. I'm looking for where it's positive. Well, this entire graph is positive, so our solution here is from negative infinity to infinity. So what we really need to consider when we have questions like this that give us a negative discriminant, it doesn't necessarily mean there's no solution. We need to consider, does my graph open up or down? And then we need to consider also, am I looking for where it's positive or negative? All right, so what we're going to do now, we're going to transition. That was from our paradigm class. We're going to transition and do some systems of nonlinear equations. So what I mean by systems of nonlinear equations, I mean parabolas, circles, and lines, any form of those intersecting. So some possible cases here. A little bit more involved than just our lines. With lines, we basically had no solutions, infinite solutions, or one solution. So it is still possible to have no solution. Whether we have a line and a parabola that have no solution, or we have a parabola and a parabola with no solutions. Those are all possible. We also could have one solution. So with a line and a parabola, one solution could look something like that. With a parabola and a parabola, could look something like that. But basically, for both of these cases, where it intersects would be the point where it's tangent. So the point where it intersects would be that point where it's tangent. Now, it's also possible now to have two solutions, and this is something we didn't see with lines. So if I had a parabola and a line, it's easy to have two solutions. If I have two parabolas, I could have two solutions. All right, then we'll look at some cases with circles. Okay, so if I have a circle, it's also possible for there to be no solutions. Whether it's a line in a circle or a parabola in a circle, it's very possible for them to not intersect. We could just have one solution. So if I have a circle and a line, that could have one solution if it's at the point where it's tangent. Also, same thing with a parabola. Okay, we could have just that one point right there where it's tangent. We also could have two solutions. So if it's a circle and a line, two solutions would be with the secant line. And if it's a parabola, again, it could have two solutions there. What's also possible, though, would be if we had a circle and a parabola, we could have possibly three solutions. So if the vertex is on the circumference and it opens into the circle, that could give us three solutions. It's also possible for us to have four solutions in this case if it opens outside of it like this. So a few different cases here. Now, something else that's possible, we're talking about one solution. With other solutions with parabolas, if I'm dealing with a horizontal parabola and a vertical parabola, that also introduces the possibility of four or three solutions. But if we're just dealing with functions, then we'll typically have either no solutions, one solutions, or two solutions if we're dealing with two quadratics. But once we start introducing those horizontal parabolas, it can create some different things. All right, so we're going to start just by graphing, just to review how to actually graph these and what's actually happening. So I'm going to graph this parabola. So this parabola, if I want to find the vertex, negative b over 2a. X-coordinate is 1. Plug that in. So 1, negative 1 is my vertex. No stretches or compression, so it follows the same pattern as the parent function. So there is my quadratic. Then I'm going to graph the line negative 2x minus 1. And I'm going to actually draw the correct vertex on my parabola. Sorry about that. That's going to be a negative 2. There's a better parabola. Sorry about that. All right, so then from there, I'm going to go ahead and graph my line negative 2x minus 1. So there's my y-intercept. There's my slope. And even though, just keep in mind, that point, I know it's hard to graph, it doesn't actually touch that point right there. It doesn't touch the parabola. Because this line is actually tangent to that parabola, the only place where it touches is right there at 0, negative 1. All right, look at the next one. We've got two parabolas. So the first one has a vertex of 1, 1. It's been compressed by 1/2, and so I'm going to go over 1 and up 1/2, over 2 and up 2. The second one also has a vertex of 1, 1, so we can see the intersection pretty clearly. It's been reflected and stretched by a factor of 2. So in this case, there is one solution, and that solution is at 1, 1. That's where the intersection is. So these, it's kind of hard to do by graphing, as you can tell, because it's hard to kind of see those intersection points unless they're pretty exact or something on the vertex. So a lot of these we're going to solve algebraically. So when we solve algebraically, we can still use elimination or substitution, just like we did with regular systems. Just a few things to keep in mind. If you solve by elimination, what I don't want to do is multiply this whole thing by negative 2 and try and eliminate the x squared. That's not going to help us get where we're trying to get to. What I'm going to do instead is eliminate an entire variable. So in this case, it's going to be really easy to eliminate the y's because they're already eliminated. So that gives me 3x squared minus 3x equals negative 2. So now if I want to solve this, it's just quadratic. So I would get negative b plus or minus the square root of b squared minus 4ac all over 2a. And you'll notice that, again, our discriminant here is going to be negative. If our discriminant is negative, we are not going to have any real solutions, which means these two graphs will not intersect. All right, looking at the second one. This one may be easier to solve by substitution because I already know what y is. Well, then substitute it. So 4x plus 8 equals negative x squared plus 4. And then this is just a quadratic. This one can factor. So my only x value here is negative 2. Take that x value, plug it into either equation, and I have my solution. Now, when it comes to running your solutions for these, it's sometimes easier to write these ones as coordinates just because we want to make sure that we have the correct x paired with the correct y. Because when we have more than one x value, we need to make sure that we get the right corresponding y value to go with it. So either box them together or write them as an ordered pair. So this is a case where there's just one solution because, again, when I substituted and solved, I only had one possible x value there. All right, so now let's look at this one. Again, we can use either elimination or substitution. We'll go ahead and use elimination because those y's already eliminate. So 3x squared plus 4x equals 0. And in order to solve this, it's easiest to factor. GCF comes out. So once it's factored, my possible solutions here are x equals 0 and x equals negative 4/3. So then from this point, take your x, plug it back into either of the two originals. So if I take x and substitute it there, well, 0 squared plus y equals 2 means that y equals 2. What's important to understand is that y equals 2 only when x equals 0. So again, I want to either box them together or I want to write them as an ordered pair because we need to make sure that we know that 0, 2 is not the intersection. Negative 4/3 2 is not an intersection, so it can't go with it. To get the y value that goes with negative 4/3, I have to substitute that one in as well. So if I do negative 4/3 squared, then I get that 16 over 9 plus y equals 2. So that would be 18 over 9 minus 16 over 9, which would be 2 over 9. So then my other intersection would be negative 4/3, 2 over 9. All All right, then our last one is going to be a case where we have a circle that is intersecting this line. So x squared plus y squared equals 10 is a circle. So again, I can either use elimination or substitution. I'm going to go ahead and use substitution because it's going to be kind of hard to eliminate when one of them's squared and one of them's not. So what I'm going to do is plug that in. And then I'm going to go ahead and solve. So I get x squared. This would be 9x squared minus 60x plus 100. Combine our like terms. And then since I'm solving here, it's okay to go ahead and divide by 10. I don't need to factor the 10 out because I'm not dividing, or I'm not, it's actually an equation. So if I divide everything by the same thing, it doesn't change the equation here. So this would be just x squared minus 6x plus 9. So this would be x minus 3 squared. So the only x value that I get here is 3. Well, then I take 3, plug it back into either of those two equations. We'll go ahead and plug it in here. So I would get that y equals negative 3 times 3 plus 10. So when x equals 3, I get that y equals 1. So 3, 1 is the solution to this system. So this would be a case where you have a circle and you've got your line going through it, touches in two, or sorry, doesn't touch in two places. It's tangent at 3, 1. All right, so that is it for quadratics. The last thing we're going to do with quadratics next class is we're going to look at some applications with the calculator and regression.